Hello, how's it going? Welcome to part B of our lesson. Polynomials, evaluating, solving, function notation, roots. This it's funny because this particular lesson is based on about a paragraph of the textbook. It's in chapter 4.1, but I find myself laying out the groundwork for a lot of conceptual stuff that's going to come up a little bit later in the course. So it's important that we take our time with these really basic things. This is the first time you're seeing some ideas, and these ideas are going to become, fairly common. You're going to see a lot of them. So, if you have any, let's start. The learning objectives here, we want you to be able to, at the end of this, evaluate a polynomial at a given input. I guess understand what we mean by evaluate and input. We want you to be able to interpret what function notation is. We'll get to that in a second. It has to do with the names we gave it and those parentheses and the x. Can you describe what we mean by solve? In other words, when we say solve this equation, I'm not actually going to ask you to solve anything yet, but we need you to understand exactly what we kind of mean, and also what we mean by root. It's something that I mentioned at the end of the last lesson, and let's go. So there's a thing that you hear more and more about, which is that as we advance, as our culture advances technologically, things often innovation is. So in other words, our technological framework is used metaphorically to describe other things. So you say, oh, the brain is like a computer. If you talk to somebody who didn't know what a computer was, they'd say, what are you talking about? It doesn't make sense. But yeah, as our technology evolves, so does our framework to different points. And anyway, so polynomials are often described as machines to whatever, and I want you to understand what I mean by that. Essentially, just imagine here you are walking on the street, and you came up to a machine. What's a machine? It's a big box. Okay? And on the box there's a number pad, 1, 2, 3, etc. And then there was a great big screen. Okay? And so what you do here is you type in numbers, and then after you type in a couple numbers and you press the big, I guess it needs to be red, you press the big red button, some other number shows up on the screen. That's all I mean by machine. It essentially, with machines, with computers, we're used to the idea of an input and an output. So you put a number into the machine, or you put some information into the machine, and the machine or computer spits out another number. Okay? So essentially, that's kind of what a polynomial does. A polynomial represents the relationship between these two numbers. You give the polynomial a number, x equals 2, and it spits out a number back at you, 7, which is meaningful in some way. A polynomial might represent, say, the number of ducks on a pond per hour, and so you could type in, well, if it's hour number 3, how many ducks are there on? And then you put it into the polynomial and calculate it, and the polynomial says 7 ducks, right? It's not. Polynomials are very generic in terms of their theoretical, what they do and what they're used for, because they have so many uses. And so us describing what they are and how they're useful is kind of a tricky thing. But I tend towards this kind of input-output way of thinking about it. You put a number in, you get a different number out. Sometimes it's the same number, sometimes it's a different number. Okay? Let's not get too weird here. what do I mean by all this? I mean, here's a polynomial. X squared minus 4x plus 12. Okay? This is some polynomial. You've been given this by your boss. You choose an input. You put this number into the polynomial and you get a number out. How does that work? I'm going to replace the x's in the polynomial with this number. Fill in the blank. 3 times 2 squared minus 4 times 2 plus 12. And then I get my calculator out and I calculate the value of each of these terms. 12 minus 8 plus 12, and then you add them all together. Minus 8. So 2 is the input, minus 8 is the output. Does that make sense? Let's try it with a different number. The idea being that, you know, different numbers will get you different outputs. How about x is equal to minus 1? Okay. You don't usually put parentheses around the input. So this becomes 3 times minus 1 squared minus 4 times minus 1 plus 12. Minus 1 squared is 1, so this first term becomes 3. Let me write this as minus 4 plus 12, so this becomes 3 plus 4 plus 12, which is equal to 19. For the input minus 1, the output of the polynomial is 19. And that's what I mean by a machine. It's just a machine that turns some numbers into other numbers. And if you can come up with a better metaphor for me to explain this right off the bat than machine, I will be very happy, because calling it a machine is weird. Okay. So, we might want to write out, you know, your boss essentially says, hey, it's your boss. Bosses have mustaches. He is, hey, figure out what the output of x squared plus 2x plus 1 and 2x plus 3 are for inputs x is equal to 1 and x is equal to 2. Let's say your boss tells you to do this. Why? I don't know. Your boss loves math. Actually, you know what? Things are getting kind of cramped on this page. I'm going to take a second and rearrange it. Let's move this down. Okay. So you do the calculations. X is equal to 1, so it's 1 squared plus 2 times 1 plus 1, so that's 4. X is equal to 1. 2 times 1 plus 3, that's equal to 5. X equals 2, so that's 2 squared 4 plus 1 is equal to 9. X equals 2, so that's 4 plus 3 is equal to 7. Okay, so you did the calculations. I just did right here. Right here. I did all my calculations. That is my rough work. And it's correct. How do I then report to my boss? How do I report these findings for my boss? I mean, if I want to be unambiguous, I would write for input x is equal to 1, the polynomial x squared plus 2x plus 1 had output 4. For input x is equal to 1, the polynomial 2x plus 3 had output 5. And just list all this in that way. So, there's a problem here. It's not a big problem. It's not a technical problem. It works. It's unambiguous. It's fine. It just takes forever to write all that stuff out. And it takes a while to read. It's unambiguous though. I know exactly what we're talking about. There's an input number and a specific polynomial, and that corresponds to an output number. But like I said, it's unambiguous, but it's tiring to read. So instead of that, I'm going to take advantage of the naming procedure I mentioned earlier. Okay? So earlier in the last lesson, I said that we can name, if we have a bunch of polynomials, sometimes it's helpful to give them all names. I'll call the first one f of x, and the second one g of x. I want you to remember why that there's those parentheses, f, x. There's always letter, that's the name of the polynomial. And then we always write this parentheses x afterwards. I never really explained why we do that. I said that it's important, and it is. So now this is the reason why it's important. So instead of this statement, we can just say, hey boss, we're talking about polynomial f of x. Instead of this statement, we can now say, hey boss, we're talking about the polynomial, not f, g of x. To specify that the input is x is equal to 1, I'm going to replace the x in the name with the number 1. The thing inside the parentheses, that's the input. And so I can say, when the input is equal to 1, the output is equal, the function is the polynomial is output is equal to 4. When the input for the second polynomial is 1, its output is 5. And similarly, I can write, I can write the rest of them. When I evaluate that 2, you get 9. When I evaluated, oh, sorry, get rid of that. And you went g at 2, 7. This is a shorthand called function notation. We'll get more into why it's called function notation in a later lesson, but that's what it's called. That's what I'll be calling it. The idea here is that somebody gives you essentially a bunch of different polynomials. 2x squared plus 3, g of x is equal to 4x minus 6, h of x is equal to x cubed. Okay? I can instruct you to determine what the output of a function is just by specifying which function I want you to find the output of by giving its label. I can say f, or I can say g, and then I can instruct you as to the point that I want you to use as the input by writing a number in here. So f3 means plug 3 in for those x's. 2 times 3 all squared plus 3, that's 21. Minus 1 is equal to 2 times minus 1 all squared plus 3, and that's equal to 5. G at 0 is equal to, I look at the g function, the g polynomial, and I'm going to replace all the x's with a 0. 4 times 0 minus 6 is equal to minus 6. Does that make sense to you? So it's a way of specifying, it's a shorthand that specifies which function I'm interested in you using, which polynomial I'm interested in you using, and also which point I want you to evaluate, which input I want you to use to evaluate. In other words, the letter here represents the name of the polynomial. The number here represents the input. And you write equals the output. It takes a little bit of getting used to. Function notation is actually fairly simple to use, but it's a shorthand, so it conveys a lot of information in a short amount of space, so it takes a while to get used to how to use it. Let's try some examples. So I'm going to name some polynomials here. 3x squared minus 7, and then 2x plus 4. Okay? Let's find out the values. Let's figure out these values. How are we going to do it? Well, you start by recognizing which polynomial you're talking about. The first one, we're talking about this polynomial. So what I'm going to do is I'm going to copy this polynomial out, but instead of writing x's, I'm going to write the number 2. I'm going to replace the x's with 2's. 3 times 2 all squared minus 7, and then I just evaluate it. 4, 12, 5. I'm going to copy out the polynomial. Instead of writing the x's, I'm going to write 1's. 3 times 1 all squared minus 7. So the input is 1. Alright, so 3 minus 4. So the input is 1. The polynomial I'm using is the f polynomial, and the output for that polynomial is minus 4. Does that make sense to you? Alright. 3 times minus 2 all squared minus 7. Careful with negative numbers when you're squaring or cubing them. Minus numbers multiplied by itself gets a positive number. So that's 3 times 4, 12 minus 7 is equal to 5. One interesting thing about polynomials is 2 different inputs might give you the same output. It happens. There's nothing wrong when it happens. Just keep an eye out for it. It's interesting. Let's try this one. 2 times 3 plus 4 is 10. 2 times 6 plus 4, 16. 2 times 0 plus 4 is 4. Okay? So we call this procedure evaluating the polynomial at, say, 0 or 6 or 3. We call this procedure plugging in a specific number and then using essentially our calculators to calculate the output. We call that input-output procedure evaluation. So when I say evaluate this polynomial, that's what I mean. Evaluate it at a specific number. You can't evaluate a polynomial unless you're given a number. But the overall idea here is somebody gives you a number, then you evaluate the problem. Evaluating is essentially the verb. You evaluate the polynomial to figure out what output you get. Okay. So, next. Let's go back to our person on the street with a big stupid box, number box. Here's your keypad, boop, boop, boop. Here's the number. And guess what? Your boss showed up. Bosses are always angry. And the boss says, figure out which number to type into the keypad so that the output is 4. How are you going to do it? You're just going to go up and type numbers until the number is 4. But usually the input isn't 4. Okay. What am I going on about? Anytime you have a polynomial, it's the relationship between input numbers and output numbers. You see? You put in a number and you get out a number into a polynomial. A specific polynomial. Okay? Put in a number, get out a number. So what's the deal? The deal is that there's a relationship between these numbers. And so there's going to be a certain number that you type in. Wait, let's take it back. When we talk about evaluating, you plug in, you get to choose this number, and the polynomial tells you what this number is. Which is nice, and it's straightforward, and it's lovely, and we call that process evaluation. What the boss wants you to do is backwards. The boss is telling you what this number is. He's saying he wants number 4 to come out. And so you have to figure out what number to plug in. Which input corresponds? Which input evaluates to a desired output? In this case, we're specifying the output, and we want you to figure out what the input is. Okay? We call this procedure solving. We're going to actually spend more time in the future describing exactly which method you're going to use to solve an equation. But the idea here is somebody will give you a polynomial to say, hey, this is the polynomial cx squared plus 4. Fine. Okay. And then we'll ask you, when we say solve f of x is equal to 4, when this is what the question is asking, what it's really asking for is it's asking you to find the input value x, where f of x is equal to the desired one. Okay? So what now? It's difficult at this particular second, given what we've talked about so far, to talk about any method for solving it. But you just need to understand what the problem is. It's really straightforward to evaluate a polynomial, but solving a polynomial for a certain number, that's something worth thinking through, worth figuring out, worth spending enormous amounts of time in a classroom figuring out how to do. One thing we can talk about though right now is testing a solution. So you make some guesses. Let's say we guess and we pay a guy on the internet, and the person on the internet says the solution is one of x is equal to 0, or x is equal to 2, or x is equal to -1. So how can we tell which of these are the solution? Well, the answer is kind of obvious. All we have to do is plug each of them into the function to see which of them outputs 4. So you can just try and see which one. Alright, so let's try that one, and then we'll try that one, and then we'll try that one, and we'll see what we get. 3 times 0 squared is equal to 4. Well, that's good. 3 times 2 squared is equal to, alright, so that's 4, 12, 16. that 3 times minus 1 all squared plus 4, that's equal to 7. And once you've done it for each of them, you can say, okay, that one, this input gives the output we're looking for. This input does not give the output we're looking for. This input does not give the output we're looking for. And so of these, x is equal to 0 is the solution to f of 0. Oh wait, f of x is equal to 4. Okay. So at this point in the game, we don't have any strategies for talking about solving polynomials. We'll go over some soon. But the thing you need to know is that we can test. We can use evaluation to test a specific solution. And also when you hear people talking about, hey, solve this, solve that, this is essentially what they're referring to. We're giving you the output, and we're asking you to figure out which input corresponds to that output. Okay? Okay, so one very common output that we ask you to solve for is 0. This comes up for a variety of reasons, and we'll be going through those reasons in class. But you know, you might imagine, okay, so this particular polynomial represents how much money I have in my bank account. If it's negative, then I'm in debt. If it's positive, then I have savings. At what point in time, at what value of x do I have 0 money? Am I going from being in debt to having savings? Right? So figuring out when a polynomial is 0 is actually a pretty useful thing, and it comes up so much that we give this particular solution a name. The solution to this equation is called a root of f of x. Let's get into what I mean by that. Oops. Here's a polynomial. Here's another polynomial. Here's another polynomial. Dot. Okay. So maybe I'll draw red lines between each of these. We're going to discuss them one by one, and I want to be able to refer to what I've said about each. So let's start with this one. The root is, I'll call it x is equal to minus 1. The root of this equation, this polynomial, is equal to minus 1. Solving this particular question, when is it 0, is so common that we describe roots as being a property of a polynomial. More on that a little bit later. All you need to know is polynomials can be described in terms of their roots. So the root of this polynomial is minus 1. Let's test it. 3 times minus 1 plus 3, that's minus 3 plus 3 is equal to 0. Sure enough, for x is equal to minus 1, you get the right output, 0. So this is definitely a root. Let's move on to this guy. This one has 2 roots. This one has roots. X is equal to -1, 2 is a root. Let's show you. F minus 2, so that's -2 all squared minus 4. So minus a negative number times a negative number is a positive number, so it's 4 minus 4 is equal to 0. And x is equal to plus 2 is a root. F of 2 is equal to 2 squared minus 4. Sure enough, they're both 0. So it's possible for a polynomial to have more than one root. This one has 2 roots. And I'm not saying that because the roots are both 2. I'm saying that there are 2 in number roots. It's not uncommon to see polynomials with more than one root. In fact, this one here has 3 roots. The roots here are x is equal to -2, x is equal to plus 3, and x is equal to -4. Let's see each of these. H of -2. So you don't need to actually write your polynomial in fully expanded form to evaluate it. Even if it's in factored form, you can still evaluate it term by term. So this is -2 plus 4. So the first term here is 0, and the second term is -5, and the third term is 2. But because both of these numbers are multiplied by 0, the overall answer is 0. H at plus 3, so this is going to be 3 plus 2, and 3 minus 3, and 3 plus, oh geez, I need to write nicer. 3 plus 4, so that's 5 times 0 times 7, so that's 0. And sure enough, I mean, I guess the point I'm trying to show you here is that in its completely factored form, it's really easy to find the roots, because a root will be a term that makes this one 0, or a root will be a term that makes this one 0, or a root will be a term that makes this one 0. Does that make sense? And so the deal here is that if it's in completely factored form, it's really easy to figure out what roots are, because you can just look at term by term and say, okay, this one will make, which one will make this term 0? Which one will make this term 0? Which one will make this term 0? More on that later. So, so this is essentially the end. Well, maybe not the end. Let's do a quick review of roots. The root, I'll call it R. R. Somebody gives us a polynomial. Its root is any value of x, so that if I plug that into the polynomial, you get 0. A polynomial might have more than one root, or it might have none at all. More on that later. Alright, let's review what we've talked about. I talked about the medicine wheels. So the first thing we talked about was the different ways we can talk about a function. So there was the function name, and we could refer to a polynomial by its name. We could say, hey, we're talking about polynomial f. We're talking about polynomial g. Or we could talk about it in terms of the actual polynomial expression. Right? So if you the name is like a shorthand that you can use to save time when you're describing things. But the expression is what you plug the numbers into to do a calculation. Related to those are the input, the value of x, and if you plug that number into the function, you get an output, f of x. And all of these are procedurally related into what a polynomial does. Also, let's go back to this other medicine wheel. We were talking earlier about how there's a factored form of a polynomial and an expanded form. If it's in its expanded form, it's really easy to see the degree. Why do we care about degree? Degree is an important feature of a polynomial. It helps classify what it's going to do and how it's going to behave. But there was also this issue of roots. If your polynomial is in its factored form, it's actually kind of easy if it's in a fully factored form. If there are only terms in parentheses that are multiplied together, it's really easy to figure out what the roots are. Alternatively, if it's in expanded form, it's really easy to figure out what the degree of the polynomial is. The roots and the degree are related. It's something we'll talk about a lot much later, but the degree actually tells you kind of how many roots there could be. So a third degree polynomial can have 3 roots, and a second degree polynomial can have 2 roots, and a 9th degree polynomial can have 9 different numbers that make it 0. Anyway, so long story short, all of these aspects are what we can use to talk about what a specific polynomial is and what it does. Alright, that's the end of section 1, lesson 1b. So until next time, keep up the good work.